My name is Hao Jiaming, and my supervisor is Professor Jack Li. My final year project is doing some optimization and design about transmission transport layer protocols. Specifically, I'm doing some optimizations about the congestion control algorithm of the transmission control protocol, which limits the maximum of the packets can be transmitted from the server to the client. Basically, there's a trade-off because if you are transmitting too aggressively, then you will cause a lot of retransmissions due to the dropout uh, in the routers. But if you are not that aggressive, you are not able to fully utilize the channel. So here shows a traditional congestion control algorithm, and it uses additive increase and multiplicative decrease, but we do not use it anymore because it is too slow. So the methodology that I apply to implement this is to combine two traditional congestion control algorithms. One of them is called Cubic and the other one is called TCP Vasloop. In Cubic, it uses a cubic function to determine the behavior of the congestion windows, and the equation is listed here. Basically, um, there is a W max, which is the congestion window size before the loss reduction. You can view it as an approximation about the largest congestion window you can utilize. So by the property of the cubic function, the differentiation will tend to zero around here. So it will stay a long time at the window size 10 to W max. And after that, it will start to probing the maximum congestion window size it can utilize. And the differentiation will grow very fast. So this property enables Cubic to be a protocol that fits perfectly to the long fat channels. By long fat, it means that the large bandwidth delay product, because it is free of RTT and it can increase the congestion window size very aggressively. The next one is TCP Vasloop. The biggest change it is making is to estimate the bandwidth according to the RTTs. Because by the differences between the RTT, it can estimate the transmission delay, which is related to the bandwidth. So our method is to combine these two algorithms, and for convenience, I call it TCP hybrid. So the way we combine it is to run them parallelly, where one of the algorithms runs in reality and the other one would run virtually. They do not have any interference except that they will both use the ACKs to update their own variables, but they will keep their variables separately. Mm. So the system will keep track of both of them and switch over whenever one of the congestion window calculated by one of them exceeds the congestion window size calculated by the other. So the window size is given by this equation, and these are given by the TCP Vasloop equations. So this procedure guarantees that we can choose the larger congestion window size at any given time. And actually, you can consider that the congestion window, the congestion algorithm running virtually would use the ACKs provided uh, con, uh, by a larger congestion window size. And even in this case, if it cannot exceed the congestion window size, then it is really inferior to the other algorithm. So we choose the other one. And the benefits that this algorithm can bring is that we can fit to the channels, because actually Cubic is fit perfectly to long fat channels, and TCP Vasloop fits better to high loss channels, because it can get rid of the effects of regarding lost packets as a congestion event happening. So here's the results. We did the simulation using this topology, there's a bottleneck link in the middle, and these two links are relatively ideal to the bottleneck link because their bandwidth is sufficiently large to support the transmissions, and the only congestion will happen here. So 0 is the transmitter and 3 is the receiver. There may be multiple flows, and you can consider multiple nodes here and here. So the first test is to test the throughput. There are several situations I mentioned just now, and first one is bandwidth delay product, and the other one is loss. I omitted the case where both bandwidth product and loss are low because in this case, even TCP Reno is capable enough to fully utilize the bandwidth. So it is not quite interesting to dig out what is happening there. So these are the other three situations. The first one is the low BDP but high loss channels. Here, REST will perform better, and you can see that TCP hybrid, the red flow, the red curve is performing like to TCP VASU, the blue curve. These three experiments are did separately, but I plot them together to make the comparison. So the cubic will frequently reduce its CWND so that it will maintain a low level, but TCP VASU is able to behave like a TCP VASU. In the second situation where both bandwidth, where BDP is high but loss is low, cubic will perform better. So you can see that TCP hybrid is performing like cubic, but I have just mentioned that it will increase slowly at these stable states. So TCP VASU exceeds the window size at this state, and we can increase the throughput a little bit, but not that much. So in the third test, where both BDP and loss are high, actually in this situation, neither cubic nor TCP VASU will perform good. But the TCP hybrids accelerates the process of estimation a little bit because it limits the reduction by 30%, which is a constant given by cubic. But TCP VASU would drop directly to its estimated bandwidth. However, it is not able to estimate. It is not able to do the correct estimation because the congestion window size is too limited, and these are the throughputs in average throughputs in 100 simulations, and you can see that TCP hybrid is performing in most cases. So additionally, I also test the fairness and friendliness. Fairness means whether the flows on a concurrent on a channel can fair share the channel. This is quite important because if one of the flows increase its congestion window size too aggressively, it is not likely for it to leak any of the bandwidth to the other flow. But actually, this we can see that hybrid is doing pretty well. And in this situation, actually, there are some synchronizations happening here. You can see that they increase together and run into a congestion together. But this situation is not supposed to be detected in the real world situations, for there are some noises introduced by the systems, and the noises are everywhere. So I will do the real world tests later. And the other one is the friendliness. It means whether two flows using different algorithm can fair share the channel. And this one is for the same algorithm. This is for the different algorithms. Actually, a good algorithm is not supposed to be friendly to any of the other algorithm, because actually it is, as long as it is not inferior to others, we can win the market. And these are the tests in two of the situations I have tested. You can see the red and the green flows are using TCP hybrid, it is not losing out to Cubic or Westwood. So to conclude, the throughput is better than any of the components, and there is no significant fault in the fairness, although the synchronizations are happening, but it is still acceptable. But I think it can do better in the real world. And friendliness is not inferior to Cubic or Westwood. And one more thing is viable and acceptable for kernels, because actually some of we want to introduce some intelligence into the congestion control algorithm, but for example, the neural network. However, the kernel is not able to calculate floating numbers. Um, but in TCP hybrid, it do not have this kind of requirements, so it is acceptable for kernels. Later, I will implement the TCP hybrid in real-world systems to make more concise conclusions, and I will also try to multiplex more algorithms more intelligently. And that's all. Thanks.